So, we've been working through the integral application chapter. How's it been going for you? Do you remember? When you have a rate, integrate. Area between two curves, upper minus lower. Irregular solids. What's the cross-sectional area? Solids of revolution. Pi r squared. Washer method. Pi big R squared minus little r squared. Today we're going to find out how an integral can help us find the length of a curve. That's right, a curvy line like a sine wave or maybe this polynomial graph. Imagine if we pulled on it and straightened it out. How long would that be? Well, an integral is going to help us to find that length.
Now, before we can answer how to find the length of a curved line, we're going to figure out how in the world we would find the length of, say, like a straight line, like maybe the line y equals 3x from 0 to 4. Now, as is the case with many problems in this chapter, and in fact, many problems in math, it can be helpful to make a sketch. In fact, I always encourage you as you guys move on in math that if you're given a problem and somehow you can sketch it, you can visualize it, you never know what that might help you then to see. So we know how to graph y equals 3x. That's just a straight line. It's got a slope of 3. Of course, this particular line is from x equals 0 to x equals 4. So we can kind of now get the idea that we're actually trying to find this exact length, this exact interval. Is anything coming to mind? Do you see something that would be true about this line segment? Do you see what is right? Do you see the right triangle? That's right. All you have to do to find the length of a straight line is to think about the Pythagorean Theorem. And the Pythagorean Theorem is pretty easy to determine here because you really have your two sides. Of course, you have to do a little thinking about the y value at this point, and I hope that you would plug into your equation and determine that the y value is 12 up here. So, of course, that makes this leg equal to 12. But when it comes to finding the length of our curve, the actual question here, it's just a matter of a nice and simple Pythagorean theorem. And we're going to end up, after we square our legs, getting 160. And, of course, the square root of that will ultimately be our solution. Now, that's how you find the length of a curve. That's a straight line. So what if we had an actual line that was curved? Well, it turns out that if we did actually have a curved line and wanted to get that total length when it was straightened out, like the piece of string from the intro, we will simply use Pythagorean theorems on small intervals. It'll be as if we zoom in on that straight line so much that we end up with a lot of little straight lines, a lot of little hypotenusae, and you'll find out that we'll be able to integrate, that is to add up all of those little hypotenusae and get a total length. Now, pretend with me that we have a curve. We're trying to find its length from A to B, and we actually zoom in on a small arc along this curve. Now, I'm going to draw the arc a little bit larger than technically it would be, because technically it would be infinitely small. But I want you to think of this arc. I want you to think of this arc as being the hypotenuse of two legs, that is a change in x or delta x and a change in y or a delta y, which then if we run the Pythagorean theorem, we could say that that arc is really nothing more than just the square root of this little delta x squared plus the delta y squared. And so if we want to get the total length from A to B, that total length would be the integral, because an integral is going to allow us to add up all of these arc lengths. So if I do the integral of this arc, that is the integral of the square root of delta x squared plus delta y squared, I'll be able to have the total length. Now, how in the world are we going to integrate something like the square root of delta x squared plus delta y squared? You might imagine that these delta x and delta y's can turn into dx and dy's, but we have another problem here. We seem to have x's and y's in the same integral. So let's do a little magic on our arc formula. Now, before we go any further, just don't forget that this square root statement is simply the hypotenuse of one of these little arc lengths. What we really want to do, though, is we want to change the form of this so that it can be plugged into an integral. Now, a couple things I'm going to do here. I wouldn't expect you to say, oh yeah, Mr. Naylor, why don't you multiply the top and bottom by delta x? I more want you to realize what happens when you multiply the top and bottom by delta x, and that is that you are able to start to transform this square root. You see, we're able to bring the delta x in the denominator into the square root if we change it to a delta x squared. Now, why did I want to bring that delta x into the square root? Well, because now look, you're able to actually do some simplifying. You're actually able to start to reduce the variables that you have. Namely, you can get a 1 plus delta y squared over delta x squared. And why would we do that? So we can pull the square out of our change in y over change in x. And why would we do that? Well, we're almost at the heart of the answer, and that is we end up with the change in y over the change in x. Now, where have you heard the change in y over change in x before? That's right, it's the derivative. We can actually change this equation to be, by the way, we'll change this delta x out here also to be dx, but we change this equation to now be in a form that uses calculus variables that we understand. And now when we integrate this, that is when we do the integral of this statement, we actually have variables that we're able to define. So check this out. The length of a curve will end up being the integral from a to b of a square root of 1 plus the derivative squared. That's going to ring, that should ring in your mind a little bit. That's a formula, and it says that the length of the curve is going to be the integral of the square root of 1 plus the derivative squared. Pretty interesting how that came from the Pythagorean Theorem. And a little bit of this and a little bit of that, we end up with a formula that we actually can compute its value using integrals. Now, it usually doesn't take students too long to find out that we're actually going to be doing an integral and a derivative in the same problem. Yep, that's correct. We're going to be doing an integral and a derivative in order to get the length of a curve. All right, so how about the length of the sine wave? Maybe it's going to end up being some kind of cool answer since trig functions just got that going on. Let's see about the length of the sine wave from 0 to 2 pi. Now, there is going to be a suggestion in these problems to make a sketch. You'll find out a little later that sometimes the sketch tells us something that requires a bit of an adaptation to our rule. So here we have the sine wave from 0 to 2 pi. It would be as if I'm trying to straighten this thing out and get its length. According to the formula, we're going to need the derivative. You'll find that usually students will figure this out first. So the derivative of sine is cosine. And now you can plug this information into your length formula. It's actually kind of nice. It's just a formula, so you can trust it. It's the integral from 0 to 2 pi of the square root of 1 plus the derivative squared. And this is in terms of x, so it'll be a dx integration. Now, how do we do this? The integral of the square root of 1 plus cosine squared? Well, the truth is that you have to use f and I and t. You can't use a substitution method, although we might want to try to make u equal the inside. There's nothing on the outside that's going to cancel with that. And so, yes, it's a problem that is unable to be integrated without f and I and t. I encourage you to type it in. It does take careful consideration of all the pieces of the formula. One of the things that we want to be careful about is that you always get the square. Using f and I and t, you're going to need a parenthesis that actually closes off the parenthesis from the square root, and then comma x, comma 0 to 2 pi. It does take a little while to compute. I don't know, 6, 7, 8 seconds, because it's actually adding up all of those little line segments to end up getting that total length of 7.64 units. All right, how about the problem that we started the lesson with? How about the length of y equals 3x from 0 to 4? Now, we already found out that we can find this length just by setting up a right triangle, but I thought we would use the formula and see if we get the same answer. Now, the formula is going to require the derivative, so you might as well find it. It's usually what people do first. So the derivative of 3x is 3. And then your length formula says that we can integrate from 0 to 4 the square root of 1. There's always a 1 there. And then it's always plus the derivative squared dx. Of course, that'll be the same as 3 squared. Now, it would make sense to simplify this because you can. So we actually end up with the square root of 10. Now, you could plug this into f and I and t, but this is a good problem to think about doing by hand because the integral or the antiderivative of the square root of 10, of course, would be the square root of 10 with an x beside it from 0 to 4. So all I really need to do is plug in 4. Technically, I'm supposed to plug in 0, but that's going to come out to be 0. And when you subtract those numbers, you're going to end up with just 4 root 10. Well, 4 root 10 is the same as 12, 6, 4. So we end up with the same answer. The formula, as I'm sure you're not surprised, works. Now, here's a problem that initially looks pretty normal, but it actually has a catch to it. In fact, the next 3 problems we do will each have a little catch, which we will make a remark on. But let's figure out first by looking at the graph of this problem what it is we need to watch out for. Now, I wouldn't expect you guys to know the graph of x tangent without your calculator, but you should have an idea that the tangent graph from last year has these branches that are separated by vertical asymptotes. So as you look at this problem a little more closely, we need to be aware of what it is we are seeing. And again, we are seeing the reality of vertical asymptotes from 0 to pi. Now, what does that mean for the length of a curve that's going to go up forever or have come from down forever if we're trying to find the length of the curve? Well, it means that it's not going to exist. There's no way you're going to be able to measure the length of the curve that goes to positive or negative infinity. So if an interval contains a vertical asymptote, then the length is definitely undefined. Now, this seems like too good of a problem to waste. So what we're going to do is we're going to change the interval to only go from 0 to pi over 3 so that we can actually find the length of this much reduced curve, but nonetheless we can find the length of this curve without the asymptote. Just by the way, you wouldn't just change a problem. I'm simply changing it so we can actually use the formula with x tangent. So that means it's time to find the derivative. Kind of neat going back and finding the derivative of something like x times the tangent of x. How do you find the derivative of x times the tangent of x? That's right, use the product rule. So it's going to be first the derivative of the second. The derivative of tangent is secant squared plus the second, the tangent, times the derivative of the first. Of course, that's just 1. So we have ourselves a derivative so that we can plug it into the integral of the square root. It's always 1 plus the derivative squared. And of course, now it's from 0 to pi over 3. Now, doing the integral of the square root of 1 plus x secant squared plus tangent, the quantity squared, is quite challenging, even using f and I and t. And so, to be 100% honest, the other piece of this problem is just being able to use your calculator. And I want to show you a little trick where you take this derivative, this somewhat complicated derivative, and you actually plug it in, you actually type it in to the y equals screen. You type it in for y1. And what happens is that ends up being a little storage spot for this equation that we can then recall in our f and I and t command. Now take a look at what I did here, and I really encourage you to do this. In the y equals screen, I typed in the derivative. I typed in the secant squared very carefully as 1 over cosine, but I am using the y equals screen as a storage spot for this complicated equation. Now, a very careful typing of the f and I and t formula, I can actually just type the square root of 1 plus y1 squared. Now this y1 symbol here came from the vars menu. You have to push the vars button and then hit, vars, yvars function. So you go to vars, yvars function, and you'll find that y1 symbol, which then can take the place of that complicated derivative. Now, if you're going to do this, which I really recommend that you do, make sure you're still sensitive to the parentheses required with the square root. Don't forget your square. And, of course, we changed the problem to go from 0 to pi over 3. So you should be able to get 2.24. So what about the length of x squared plus y squared equals 9? As negative 1 is less than or equal to y is less than or equal to 1. Uh-oh, we got a couple things going on here. First of all, we got an equation that's maybe not just the regular old graph that we're used to. And you got to notice that this interval is given in terms of y. All right, well, first things first, it's usually recommended and helpful to think about a sketch. Now, if you're saying, but Miss Naylor, I don't know how to sketch x squared plus y squared equals 9, maybe we have to go back to the recall and remember from last year that that's a circle. Now, if you don't remember that that's a circle, you could always solve this equation for y equals in order to put it in your calculator and graph it. But I'm going to use the knowledge that x squared plus y squared is a circle that has a radius of 3 to help us to be able to get this graph drawn. Now, we want to focus on the interval as we move forward here. And it does say that y is less than 1, but greater than negative 1. Now, y less than 1, well, y equaling 1 is going to be way back here. So here's our y value of 1, and we could say that the y value of negative 1 symmetrically would be about here. Are you starting to see what it is that we're actually trying to find in this problem? We're actually trying to only find the length of these two sections of this circle. These are the only two sections where y is between negative 1 and 1. But maybe even more importantly, what's ultimately going on in this problem is that it is in terms of y. That is, when we actually get to the point where we want to set up our integral, we're going to end up using y values right here, and we're going to end up needing to have a dy integration right here. Now you say, well, what's the big deal about that? Well, it turns out that what that means is that your derivative will actually end up being upside down. Instead of being dy dx that we're used to saying, it's actually going to have to be a dx dy. A dx dy derivative is no different than a regular derivative, except the equation that it came from. You see, the equation that it came from will have to be solved for x. So we take a few steps here and we rewrite this equation to be of the form of, well, let's just take the square root of both sides at the same time here. So we're going to solve this equation for x so that it can be of the form the square root of 9 minus y squared. Now what I want you to see is that since the interval was given in terms of y, that we had to solve this equation for x so that we could switch to a dx dy derivative in order to form a dy integration. Okay, so this is a little something special about this problem. And again, you're going to say, well, how am I supposed to know this? And I'm telling you, because the interval was in terms of y, it tells us that we're going to end up switching this problem. The whole problem is done in terms of y. Now, we need to do the derivative of this x equals equation, and remember, it's a dx dy derivative. Really what we need to be asking ourselves is how you do the derivative of a square root. I hope that you're thinking about 1/2 powers, because that's the same as a square root. And as I journey on my way to do the derivative of the outside and leave the inside alone, that's right, I'm actually doing the chain rule. So we're going to end up having to multiply by the derivative of the inside in order to get our full derivative, which ultimately has a little bit of simplifying. And if you would like to write it as far as a numerator and a denominator, you may do that. If I choose to, I can rewrite this as, since it's a negative exponent, as a square root in the denominator. Now, ultimately, this derivative is what I'm going to plug in here to my formula, which says, of course, the square root of 1 plus that derivative squared. Another excellent opportunity to use that little calculator trick where you type this derivative into the y equals screen. Yes, you'll have to use the x button, the x variable, when you type it into the y equals screen. The calculator doesn't really care what variable it is. It's still going to compute the integral using f and I and t just the same. Notice here, too, that I plugged in the y values when I used f and I and t. Make sure you can get your calculator to do this. And make sure that you also realize that there's one other small little detail going on in this problem. It's more of an algebra idea, but way back here when I solved this equation for x, I ended up only getting or working with one square root. That is, it should have been plus or minus, but I ended up only working with one of them, which really meant that I was only finding the length of the positive side of this circle. Now, even if I had put the plus or minus there, I would not have been able to do that at the same time. So what's happening here is that this answer of 2039 is only referring to half of what I'm trying to find. Well, it's not real hard to fix it. All I got to do is multiply by 2. Now, again, the reason I'm multiplying by 2 is because I really only found the length of a positive half of this circle. But I don't want to forget about the plus or minus, and I can take care of that with just a little times 2 to get my total length of both sides of this circle. Now we've got one more problem to do, and you might remember me saying that there's going to be one more little catch. But if you look at the length of y equals x to the 1/3, from -8 comma -2 to 8 comma 2, well, it seems like we have x and y values being used. Now, you're going to learn that these problems they start to boil down to knowing if I'm supposed to do the problem in terms of x or in terms of y. For this particular problem, it seems like that I might have the option to do it both ways. Well, first off, let's look at the graph of x to the 1/3. Now, x to the 1/3 is actually two sides of a radical graph, and -8, -2, and 8 to 2 would be its endpoints. It doesn't look like there's any funny business with this graph, so why don't we proceed with the derivative? And the derivative of x to the 1/3 is just a nice little bring the exponent down and subtract from the exponent. Just a word of caution, make sure you're doing the derivative here. That is, that you're actually subtracting from the exponent. that as opposed to adding. Now, when I'm ready to do the length of the curve, I should be able to integrate from -8 to 8 of the square root of, are you getting the idea, 1 plus the derivative squared. I actually don't care if you recopy the derivative or if maybe you just write the derivative symbol, but I do want you to realize that this is in terms of x, and the reason it's in terms of x is because we've done the derivative with x variables, and we're also doing the limits of integration over here with x values. So let's pop this into f and I and t. I actually like using the little y equals screen trick. It just makes it a little easier to tidy up the final integral using f and I and t. And everything seems fine until you hit enter and you end up getting an error. Now, the type of error that you get isn't because you missed a comma or missed a parenthesis. The reason you're getting an error is because of the derivative. And remember, the derivative, which is actually referring to the slope, has a problem. It actually has a problem right here in the middle of this graph. It might be a little hard to see, but there is a vertical tangent right here. In other words, the slope is undefined at 0. Now, a vertical tangent is not the same as a vertical asymptote, but a vertical tangent is referring to a slope that does not exist. So, if the interval contains a vertical tangent, and again, this would have to be something you would see visually, but if you have a vertical tangent, then you have to, once again, solve for x, because you're going to have to actually switch your derivative again to be a dx dy. Now, what this does is that it allows the 0 that was once in the denominator to now be in the numerator. It actually switches my slope so that I'm not dividing by 0. And so we'll end up doing another dy integration. Now, that means that you have to actually take your equation, you have to solve it for x. I would have to raise both sides to the third power so I can rethink this equation as x equals y cubed. But the real reason I'm doing that is so now I can do the derivative as a dx dy. And business as usual, I can bring down the exponent, get a 3y squared for my derivative. But when it comes time to do your integral, we're going to have some significant changes. That is, we're going to now pick the y values from our points, and my derivative is technically a dx dy. Of course, my equation is now, my integral is now a dy integration. This is a good problem to actually put into f and I and t, as they all are. It'll force you to realize that, yes, you're typing in 3x squared, you're typing in the dx dy derivative, and you're using the y values as your limits of integration. And we end up with now a defined value of 17.261. So generally speaking, the length of a curve concept is pretty straightforward. It's just the square root of 1 plus the derivative squared. But you do have to be careful where sometimes you have to actually switch the way you do the problem. Honestly, both of these situations refer to a graph that is a little bit more sideways. And so you want to be looking for graphs that might appear to be sideways, because if you have a graph that is not actually a function, well, you're likely to have a vertical tangent. And whenever you have a vertical tangent, it just means that you have to do the problem in terms of y. Both of these situations are in terms of y, so that you don't get an error when you try to calculate your integral. So you're ready to start your assignment, and as always, do a great job.